The last video in our transformations unit is all about symmetry. You've probably heard this term before, maybe in an art class. We're going to talk about the different types of symmetry here. So we first have a line of symmetry. A line of symmetry is any line that you can draw in a figure that cuts the figure into two congruent parts. So we're going to look at a couple of shapes here and talk about where exactly all the lines of symmetry are. So in an equilateral triangle, that means all the sides are the same. I can actually draw three lines of symmetry. And those lines of symmetry, if you imagine if I were to fold, if you cut that out as a piece of paper and you were to fold it, it would fold nice and evenly onto itself. Whereas in an isosceles triangle, if you recall, that means these two sides are congruent. I can't draw that line of symmetry, because if I fold along that line, you can tell this section wouldn't perfectly match with that. So this one only has one line of symmetry. And the line of symmetry just goes sort of right down the middle here. A square has lines of symmetry here, here, and across the diagonals. Whereas a rectangle, another quadrilateral, only has two lines of symmetry, here and here. A lot of students want to say that it has a line of symmetry here. But if you actually try to fold, like just use your piece of paper, if you try to fold a piece of paper along the diagonal, it doesn't match up perfectly. And so that makes it not a line of symmetry. So here are some problems that we kind of can look at based on symmetry. So it says the line of symmetry for a quadrilateral is at x equals -1. So x equals -1 is this line right here. So we're saying that's the line of symmetry. That's the line that cuts this figure perfectly in half. And we have quadrilateral ABCD. So we have to go A to B, and then from B, we have to go to C somewhere. So this is actually just like a line of reflection. So we're just going to count how far away. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that's where point C would go. So that's at the coordinates 1. That's at the coordinates 4, 2. And then point D, same thing with A. 1, 2, 3, 1, 2, 3. And that's where point D would go. And then we can just draw that figure in. So point D is at the coordinates 2, 5. This one here, it says find the coordination, I think I should say, of point D given that the figure is symmetric about the x-axis. So it's telling us this is a line of symmetry. And so essentially, kind of going to do the same thing. We're basically just going to say if this sort of folded over, where would this point go? And so if this folds directly over to here, notice what happens. This would just be at the point -2, +4. Because now I'm up in the positive y values. Rotational symmetry. Rotational symmetry is when a figure can be rotated around a central point and it still looks exactly the same. Meaning if I have this star and I rotate it, that this point here kind of goes to the top, that the star looks exactly the same, I didn't really change it. So what you kind of want to do for that, or for these types of problems, is kind of look for how many sort of key points do you have within your figure. So here we have 1, 2, 3, 4, 5. It's a 5-pointed star. And now we're basically just going to do 360 divided by 5. 360 divided by 5 is 72. So this has 72-degree rotation. But you also want to continue that by just keep adding 72. So if I take 72 plus 72, that tells me it's also 144. It also keeps adding to 216, and then it also adds to 288. And if I add 72 one more time, that puts me at 360. You don't have to say 360 because every figure has 360-degree rotational symmetry. So this figure here is a little bit more complex. So we kind of have a curvy part and a pointed part. So we really only have two pointed parts. So this particular figure only has 180-degree rotation. If I flip my paper sort of upside down, it would still look the same. This one here has 6 points, so we can do 360 divided by 6, and that gives us 60. So this has 60-degree rotation, but remember we have to continue to add 60 basically until we get to 360. And that's how it stops. So the kind of interesting thing about this is we said 5 and we had 4 rotational symmetries, 6 and we had 5 rotational symmetries. So that's kind of another indicator of that. For this point here, this figure is kind of tricky. I think it looks a little smushed in the video here. On your paper it might look a little nicer. This should be sort of distributed evenly. So we have sort of a 4-point star. So 360 divided by 4, that gives me 90, add 90 again, add 90 again. So those are my rotational symmetries there. This one here is always a good time. We have 1, 2, 3, 4, 5, 6, 7, 8 points that we can turn about. 360 divided by 8 is 45, and then we just keep adding 45. 90, 135, 180, 225, 270, and 315. So we have 7 rotational symmetries. Last thing we will discuss is point symmetry. Point symmetry essentially is if a figure has 180-degree rotational symmetry. So it basically looks the same and it's going in the same direction. So this one here says determine whether a figure has point symmetry. In other words, if I rotate it 180 degrees, does it look exactly the same? So this particular figure, if I rotate that 180 degrees, yes. This particular figure would not look the same, because if I rotate it 180, it sort of ends up pointing in a different direction, and so this one would be no. Does this have 180-degree rotation? Yes, it does. Does this figure? No, because if I rotate this, the big part ends up on the bottom and the small part ends up on the top, and that does not work. Okay, those are all of your transformation videos. Thank you for watching.